So in the previous class, I told you the intrinsics about the intrinsic semiconductor. What is the intrinsic semiconductor? For the intrinsic semiconductor, which is found naturally in the nature, right? So that is called the intrinsic semiconductor, and we have seen that the conductivity of the intrinsic semiconductor is very less, and the semiconductor in pure state, it is useless, right? So what we have to do, we have to modify the conductivity of the semiconductor, intrinsic semiconductor, by adding some impurities atom, and that phenomena is called the process is called the doping. Are you getting or not? So doping is the process by which some impurity atoms are added into the intrinsic semiconductor so that we can increase the uh, conductivity of the semiconductors. Are you getting or not? So that phenomenon, that is called the doping, and the atoms which are pure, which are used as an impurity atoms, are called dopants. Are you getting or not? So you can write the few lines, you can write the conductivity of the conductivity of pure semiconductor is very less, and therefore no, it is useless, right, it is useless, intrinsic semiconductor are useless, right? So to increase the conductivity to increase the conductivity, we have to add we have to add we have to add some impurities, right, some impurities, and this process is called, what is process? To adding the impurities in the intrinsic semiconductor, this process is called doping. And the atoms which are doped, atoms which are doped which are doped doped are called dopant, right, dopants. And these dopants are of two types. These dopants dopants are of two types, right? What are the dopants? Pentavalents, impurity, pentavalent, or trivalent, right? Pentavalent impurities like the arsenic, antimony, and phosphorus, and the trivalent impurities are like indium, boron, and aluminium. The arsenic or phosphoric you choose, right? There are 5 electrons, right, in the uh, outermost shell. In the trivalent impurities, there are 3 electrons in the outermost shell, whether it is indium or antimony, like this. So the pentavalent mean the 5 electron in outermost shell, the trivalent mean the 3 electrons in the outermost shell. So there are the two types of the dopants we are going to use to increase the conductivity of the semiconductor. Are you getting or not? Copy this. So when you added the impurities, the pentavalent or trivalent, the semiconductor are obtained. Those semiconductors are called. So the semiconductors with impurities, are called extrinsic semiconductor. And they have good enough conductivity for conduction of electron, conduction of current, right? Conduction of current. And these extrinsic semiconductor are two types, right? two types of semiconductor, two types of extrinsic semiconductor and extrinsic semiconductors. First, the N type, and second is P type. Listen one thing. When the semiconductors are silicon or germanium, elemental semiconductor we are considering, when the pentavalent impurity is added to the N-type semiconductor, to the intrinsic semiconductor, the semiconductor obtained is the N-type. If pentavalent, you may write, when pentavalent impurity is are added to intrinsic semiconductor, right? So the semiconductor is N-type semiconductor, and when the P-type semiconductor, when the trivalent impurities are added to intrinsic semiconductor. So the semiconductor is called P-type semiconductor, right? Pentavalent mean the phosphorus, arsenic like this, or antimony, and the trivalent mean boron or aluminium or indium, right? So there are two types of the extrinsic semiconductor we are going to discuss, the N-type and the P-type, according to the impurities atom added to the semiconductor. Copy this. So first we will discuss the N-type semiconductor, right? Okay, so I will discuss the N-type semiconductor first. First is N-type semiconductor. N-type semiconductor. What is the N-type semiconductor? Listen one thing. In the pure semiconductor, silicon is over there, right? And in the this is the pure semiconductor or intrinsic semiconductor. Now what we do, we will add the trivalent impurity, we will add the pentavalent impurity, and we will replace one atom by the pentavalent impurity like phosphorus, right? So if you remove this silicon atom by the if you replace this silicon atom by the phosphorus atom, so what will happen, you tell, right? So the silicon, every silicon has the 4 atoms, 4 electrons in their outermost shell, like this, all right? But the phosphorus has the 5 electron in the outermost shell. So the 4 electron of the phosphorus make the covalent bond with the neighbor silicon atom, like this, right? Like this, right? So this is the thing, right? This is the thing. So this is the one extra electron is available for the conductivity. When the pentavalent impurity is added and the silicon atom is replaced by one phosphorus atom, so an extra electron is available. Are you getting? An electron is available which is free to move in the space of the crystal between the silicon atom. Therefore, the number of electrons are available, right, as compared to the previous one, and therefore the conductivity is increased. Are you getting or not? So can you make this figure first? Copy this. Okay, so I'm writing here one silicon atom is replaced by phosphorus atom, right? And 4 out of 5 electrons of phosphorus atom form covalent bond with neighbor atoms, and 5th electron, these 4 electron make the covalent bond with the neighbor atom, and fifth electron is available to move in the crystal structure, this free electron acts as a charge carrier. This free electron acts as a charge carrier. Are you getting or not? Listen, the energy required for this electron, the energy required to detach this free electron is very small, very less. For germanium, this energy is 0.1 electron volt and 0.05 electron volt for silicon, right? So to remove this electron from the phosphorus atom, the energy required is very less. Do you understand or not? So such type of impurity increases the number of free electrons, therefore these impurities are called donor or n-type impurities, right? Copy this. So listen one thing, when this atom is added, this electron is free to move in the crystal structure between the atoms. There is a space, this is space, right? So this is free electron. So when this is, the potential difference is applied. Are you getting or not? This is the potential difference is applied. So this electron acts as a free electron. So how many if number of impurities atom are p, right, and number of impurities are nd, so the same number of electrons are available, free electrons are available, which increases the conductivity. Listen one thing, when you added, for example, if you consider the Venn diagram of the intrinsic semiconductor, right? Intrinsic semiconductor. So this is the valence, this is the conduction band, and this is the valence band, right? So the energy gap is, although it is less than 3 electron volt, but at the room temperature these electrons are not available in the conduction band. But when you add the n-type semiconductor, n-type semiconductors, right, n-type impurities are added, n-type extrinsic semiconductor, in that case, when you add the impurity atoms, an energy level of the phosphorus is introduced between the conduction band and the valence band. So although for the pure semiconductor there is large energy, much more energy required for this electron to move in this conduction band, but when the phosphorus energy level is introduced, so the energy is very less. How much it is? 0.01 electron volt for germanium, and if this is the silicon, so how much energy is only required? Only 0.05 electron volt. while in case of intrinsic semiconductor is it less than 3 electron volt, and it is 0.05 electron volt. So what is the benefit of adding this phosphorus atom? How many phosphorus atoms are added, so the same number of electrons are available in case of the in the conduction band. Are you getting? Therefore number of electrons are increased, number of electron are increased for conduction of the current, for conductivity. Do you understand or not? You tell. So when you added the phosphorus atom, or when you replace the phosphorus atom, when you replace the silicon atom by the phosphorus atom, a discrete energy level is introduced just below, this is the phosphorus, just below the conduction band, and electrons are increased for the conductivity. Are you getting or not? Copy this. Number of electrons are increased, right? Number of electrons are increased if, listen, Nd is the what number of donor atoms. Are you getting or not? Number of donor atoms. So what is the number of electrons? The electrons carrier concentration is equal to the number of donor atoms. Are you getting or not? How many electrons are present initially? When before adding the phosphorus, the electron and holes were, if you consider, only the silicon was there. So here one bond is broken, the electron and hole. So in this case, the electron, when for the intrinsic semiconductor, for pure semiconductor, electron and holes are in the equal numbers. Ne and Nh is equal to Ni for the pure semiconductor. But when it is replaced by phosphorus, so an extra electron is over there. Are you getting or not? So how many donor atoms you add as an impurity, the same number of electrons are available for conductivity. Are you getting? So N is the number of donor atoms are added as an impurity. So the number of electrons per meter cube will be same or not, you tell. So number of electrons is equal to the number of donor atom here. Are you getting? In this case, number of electrons per unit volume is greater than number of hole for N-type semiconductor. Do you understand this thing or not? You tell. Right. In this case, number of electrons are more as compared to the number of holes. But listen one thing. I am writing here after this, for intrinsic semiconductor, the number of electron and number of holes are equal to Ni. This is called the intrinsic carrier concentration. Intrinsic carrier concentration, which depends upon temperature. If you increase the temperature, the number of intrinsic carrier concentration is increased. Are you getting or not? But for extrinsic semiconductor, although Ne is greater than Nh, as I told you, right? Listen one thing. For the intrinsic semiconductor, if you multiply Ne and Nh, so this is equal to what? Say Ni square. Ne into Nh is equal to what? Ni square. This is called the law of mass action. You just have to remember this. It is not very much useful. The useful is that Ne and Nh is equal to Ni square. You have to remember. Are you getting or not? But for extrinsic semiconductor, Ne and Nh, Ne is greater than number of electrons are greater than as compared to the number of holes. But if you multiply Ne into Nh, it is again equal to Ni square and it does not change. That is intrinsic carrier concentration does not change. Are you getting or not? You tell. Are you getting? And the number of electrons are equal to what? Number of donor atom. So therefore the number of holes is equal to what? Ni square upon Ne, and here I can write the number of holes is equal to Ni square upon N into D. Is it clear or not? You tell. Copy this. So you tell me, for the n-type semiconductor, electron concentration is more or hole concentration is more? Electron. Hole is also present. So the number of electron will be equal to what? Yes, electron concentration will be equal to the dopant atom. Are you getting or not? And the hole concentration will be equal to Ni upon Nd, Ni square. What is Ni? What is Ni? See, intrinsic carrier concentration, it depends upon what? It depends upon the temperature. Are you getting? Okay, listen one thing. In this case, when the p-type when the n-type impurity is added, so it become n-type semiconductor. N-type semiconductor. N-type semiconductor. In this n-type semiconductor, electrons are in majority charge carrier. Electrons are in majority. Electrons in n-type semiconductor, electrons are in majority. Therefore, these are called majority charge carrier. Majority charge carrier. All right, majority charge carrier. And holes are minority charge carrier. Are you getting or not? So if you consider this the n-type semiconductor, so the electrons are present in majority, but also holes are present. These are the electrons and these are holes. Are you getting or not? You tell. Right? That is the thing. And the current is due to conduction of electron, due to majorly is due to majorly conduction of electrons. Is it clear or not? Copy this. So this is the n-type semiconductor. In the n-type semiconductor, what are the majority charge carrier and the minority charge carrier? Holes. Right. Now I will discuss the p-type semiconductor. Right. Second is p-type semiconductor. P-type semiconductor. Which type of impurities are added? The acceptor type impurity is added. Do you understand or not? Acceptor may trivalent aluminum boron. Right. For example, if this is the, you can consider silicon or germanium, the thing is same. So this is germanium. Right. In this case, one atom is replaced by the boron, suppose. Right. Suppose this is the aluminum. So here, before the impurity, every atom has the 4 electron in the outermost shell like this. Is it clear or not? This is the case. So the 3 electrons of this impurity atoms make the covalent bond with the neighbor atom, and this is the one bond is made by this. Are you getting or not? Listen, right? And listen one thing. This is the bond, this is the covalent bond, this is the covalent bond, this is the covalent bond, like this, right? No difference is over there. When the aluminum is over there, right? So one electron is deficiency. There is the one deficiency of the one electron. So this covalent bond is broken and this electron is released. So this electron comes over here and it is stable now. And the 8 electrons for the aluminum atom is over there, and therefore this is what, and vacancy is created, which is called hole or Keter. Do you understand or not? Right. Okay. One more important point is left here in the n-type semiconductor. You tell the n-type semiconductor, when the pentavalent impurities are added, they are neutral, they are negatively charged, or they are positively charged. N-type semiconductor. Neutral. Why it is neutral? In this case, why it is neutral? When the electrons are more as compared to the hole. Tell me. Why? Yes, yes, very good, very good. When the electron leave this phosphorus, so this the phosphorus, right? Phosphorus atom becomes positively charged ion, right? And therefore therefore n-type substrate is neutral. In the same way, it is not like that it is accepting the whole. So this is the phosphorus is the positive ion, right? In this case, when the electron it is accept the electron from the outside, when an bond is broken, so it become the negative ion, right? And a hole is there. Therefore, as a whole, this substrate is neutral material, neutral n-type semiconductor. Although the number of holes are greater than number of electron, but the number of electron and number of hole product is equal to Ni. This intrinsic semiconductor is there. Are you getting or not? Ni depends upon, you tell. Yes, it depends upon temperature. Although there is an expression for the Ni, but we are not going to discuss that. Also, the whole concentration is here approximately to the acceptor impurities. These are the acceptor impurities. Therefore, the number of electron impurities Ni square upon NH, right? It is equal to what? NH, and Ne is equal to Ni square divided by N acceptor. Do you understand this thing? So this is the p-type semiconductor. In this case, yes, Sanjay, in this case, which are the majority charge carrier? You tell. Yes, if this is the p-type semiconductor, in this case, holes are majority charge carrier. Are you getting? And few electrons are also present. Holes are majority charge carrier, in this case, majority charge carrier, and electrons are minority charge carrier. Do you understand or not, you tell? Please copy this. So in this case, p-type of semiconductor, if you consider the energy band diagram, right? Energy band diagram, right? Energy band diagram. What is that? Listen, if the conduction band and the valence band are like this, for the semiconductor, the energy gap is definitely 3 electron volt, but these electrons have not sufficient energy so that they can reach to the conduction band. Are you getting or not? So when you add the aluminium or the trivalent impurity, one energy level and energy discrete acceptor energy level is in, this is the acceptor energy level which has the hole, right? It has the one vacancy is absent present. Do you understand or no, or not? So acceptor energy level is added, is introduced just above the balance band, just above the balance band. Are you getting or not? Right. And this is neutral, right? Aluminium is what? This ion is dopant atom is negatively charged, and p-type semiconductor is neutral, Are you getting or not? Is neutral. Listen one thing, when an acceptor energy level is introduced, so from the valence band, actually this electron has to reach into the conduction band, but this electron is not able to cross this gap. But when an acceptor impurities is added, so this electron is just jump into this, it is easier. This energy gap is 0.01 electron volt, very less. So when the electron is jump to this acceptor energy level, this octet, the octet of the aluminium is completed, and here the vacancy is produced. Are you getting or not? So in this case, which are present, the holes are present as a majority charge carrier. Do you understand or not? Holes in the valence band, are majority charge carrier, although these holes are not physically present like electron has the mass, the holes are massless, but they are equivalent to what? They are supposed to be, they are equivalent as the proton, right? So therefore these are the holes present in the valence band, act as the charge carrier, which are the majority, which are present in the majority in the p-type semiconductor. Copy this. So we can do a one question. Suppose, for example, suppose a pure Si silicon crystal has 5 into 10 की power 28 atoms per centimeter cube, right? This is a silicon crystal, right? Silicon is present in 1 centimeter cube. How many atoms are there? If it is doped by 1 ppm. This is the unit of the doping, ppm, parts per million, concentration, right? It is doped by 1 ppm of pentavalent impurity, arsenic, right? Calculate number of electrons and holes, right, per meter cube, per centimeter cube. Are you getting or not? Given the intrinsic carrier concentration is 1.5 into 10 की power 16. So this is the question. All right, copy this. Listen one thing, this is the intrinsic carrier concentration, and suppose this is the 1 centimeter cube. So how many atoms are there? Silicon. The silicon atoms are in 1 centimeter cube. How many atoms are there? 5 into 10 की power 28. So what is the impurity? Part per million. Are you getting? It means in 10 की power 6 atoms of silicon, right? In silicon atoms, out of 10 की power 6, only one arsenic atom is introduced. Are you getting or not? So what is the donor concentration? The number of electrons which is equal to the number of donor atoms. How many donor atoms can you tell? 28 divided by 10 की power 6. Are you getting or not? You tell. Should I explain this? Yes. So the donor atoms are this, and for the n-type semiconductor, the semiconductor will be n-types because impurity is pentavalent. So it will be approximately equal to the donor atoms concentration, 5 into 10 की power 22. So this is the electron concentration, right, per centimeter cube. Now how to find the whole concentration? Ni square upon Ne. So Ni is what? The intrinsic semiconductor is this square. The electron concentration is 5 into 10 की power 22. 225 into 32 divided by 5 into 10 की power 22. Right. 5 चौक 20, 5 चौक 20 और 5 पंजे 25. 0.45 into 10 की power 10. It is 4.5 into 10 की power 9. So this is the whole concentration. The whole concentration and the electron concentration, you can check which is greater. The whole electron concentration is very much higher as compared to the whole concentration. So the majority charge carrier are electron and holes are the minorities charge carrier, right? Copy this. So you understand these things, Sanjay? ले बात करा Yes, Sanjay, you understand this thing? How to find the concentration, parts per million. Okay, so now we can move to the PN junction, right? The PN junction. Listen one thing. If you consider the p-type or n-type semiconductor, so these semiconductor has the very high conductivity as compared to the intrinsic semiconductor, but they are not used as it is. We have to modify these semiconductors again in the form of junction, in the form of p and n-type semiconductors. P and n-type semiconductor are formed in the form of junction and they are used, right? So what is the p-type and n-type junction? So if you have the p-type semiconductor, right, this is the p-type and this is the n-type semiconductor. Are you getting? So when the p-type and n-type semiconductor are added, right, so they form the PN junction, and it is very useful thing. How it is, I will explain. So what is the p-type semiconductor? What are the majority charge carrier in the p-type? In the p-type, what are the majority charge carrier? You tell. Hole. And how many holes are present? Equal to the acceptor atoms, right? So this is the, listen, this is the fixed ion, this is fixed negative ion, and for this negative ion a hole is present and this hole can be moved bond by bond, right? So if you are making the p-type semiconductor, there is a fixed negative ion and for this negative ion there is a hole. Fixed negative ion, 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 hole. Fixed negative ion, there is a hole, right? And fixed negative ion, there is a hole. Fixed negative ion, there is a hole. Negative ion, 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 hole. For every negative ion, every impurity atom is what? Say negative ion, and for this the hole is present. For this hole is present. Are you getting, Sanjay, or not? You tell. Right? In the same way, listen one thing. These are the immobile ions immobile ions, right? And this is the hole. But the electron, somewhere the electron is also present, like this, like this. These negative are ions and these are the electron. Are you getting or not? So you tell me, in the p-type semiconductor, which can move? You tell. Holes and also electrons. These ion can move? No, these are the fixed ion. The electron and holes can be moved. In the same way, if it was the phosphorus, so this is the electron present and this is the positive ion. So if you make the n-type semiconductor, positive ion, electron, positive ion, electron, positive ion, electron, positive ion, electron, 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 electron. Are you getting, Sanjay, or not? You tell. Positive ion, electron, positive ion, electron, positive ion, electron. What are the majority charge carrier in n-type semiconductor? Electron. And few holes are also present, like this. Few holes are also present. In this case, what is the majority charge carrier? Holes. And the few electrons are also present. Do you understand this thing or not? Right? These are called the acceptor ions, immobile acceptor ions, right? And these are immobile donor ions, Are you getting or not? Right? Copy this first. So listen one thing. What is the majority charger? Hole. Here in this side, holes are in majority. And here electrons are in majority. Here electrons are in minority. Right. Here holes are in minority. Do you understand or not? So therefore, due to the concentration diffusion, due to concentration difference, diffusion takes place. Are you getting or not? Diffusion takes place. What is the diffusion? Do you know the diffusion process? The movement of the higher concentration to the lower concentration. Here the holes are in majority and holes are in minority. The holes start moving this side. Are you getting? Here the electrons are in majority and electrons are in minority. Therefore, electrons start migrating from n-type to p-type. Do you understand this thing or not? Due to concentration difference, diffusion takes place. That is, holes move from p to n-type and p to n side, and electrons move from n to p side. Is it clear or not? So while doing so, the electron and holes movement takes place. The electron and holes combine each other. Right? Look at the figure. This is the junction. Near the junction, listen one thing. Near the junction, when hole move this side, so it combined with this electron, and the electrons and hole combine each other and neutralized. Do you understand or not? So when the hole move from this, so this is uncovered, ions remains. This is uncovered ions remains. Do you understand? This hole and electron combine each other. This hole and electron combine each other. Therefore, this electron and holes combine each other. So near the junction, these are the uncovered ions. These are uncovered ions, right? Uncovered ion. Are you getting or not? So again, this hole and electron combine each other and the uncovered ion form. Are you getting or not, you tell? Right? Right. But still there are, the holes are present. Holes are present. Right? The electrons are present. Are you getting or not, Sanjay? With ions, but here when the holes are present, some electrons are also there and some holes are also there. So in this region, what are they? Uncovered ions. Do you understand this thing or not? This is p-type semiconductor and this is n-type semiconductor. Please copy this. These are the uncovered ion. Therefore, listen one thing. This is the positive side, this is the negative side. You tell me, here what are the charge carrier? And what are the charge carrier? In this region, what are the charge carrier? Nothing. So in this region is called, depletion region. This region is called depletion region. Are you getting or not? You tell me, why it is depletion region? Since no charge carrier is present. No charge carrier is present. Right. Inside this, the electric field is produced from positive ion to negative ion. And the width of this depletion region is approximately 0.1 micrometer. Are you getting or not? Listen, when the depletion region is introduced, no further diffusion takes place. Why? Because after sufficient electric field is produced, this internal electric field prevent the further diffusion process. So when this hole enter in this region, because of this electric field, this is it cannot reach to the other side. Are you getting or not? So the electric field is from this left to, from right to left is over there. Do you understand? Listen one thing. This is the depletion region. So when the diffusion process is stopped, the depletion region is formed, and this is the high potential. This is the, in the direction of electric field, the potential is reduces. If you assume this is the lower potential and this is higher potential, when there is a electric field, this is V1 and V2. Which is greater and which is less? You tell. Right. So if I assume this is the zero potential, so as we move from left, from this point to this point in this way, the potential is increases. Are you getting or not? And this potential difference due to this repression region is called the barrier potential. Right. This is called the barrier potential. Barrier potential. Barrier potential due to this depletion region. Are you getting or not? You tell. And the electric field, if you make the electric field, right, the electric field is, if you assume this is the positive direction, the electric field is like this. This is the electric field. Electric field. Are you getting or not? As a distance x, the electric field is maximum at the midpoint. Here the electric field is 0, then it is 0. So this is the variation of the electric field. Are you getting or not? Yes, copy this. Okay, so this barrier potential is the potential difference which is required to, right, for this hole to jump, right, for the silicon diode, right, for silicon diode, for the silicon and for germanium, this barrier potential is zero point 0.7 volt, right, 0.7 volt, and this is 0.3 volt. Are you getting or not? And this PN junction is called, this PN junction is called diode, is called diode. Do you understand? This PN junction is called diode. This right, this PN junction is called diode, right? What is the symbol of the diode? If this is the P side, this is the P side, this is the N side, and this is the depletion region, right? In P side the negative ions are there, all right. In the N side the positive ions are there, like this, right? So this is the PN junction diode, and the symbol of the PN junction diode is this. This is the P side and this is the N side. This is the symbol of diode, right? And this is the PN junction when no potential difference is applied over here. Are you getting or not? Look, what is the width of this PN junction? Say 0.1 micrometer. If you want to find the electric field, dV is equal to what? Minus E dot dr. So electric field is approximately dV upon dr. So the distance, what is the distance? This is the 0.1 into 10 to the power minus 6. If you take the average of the 0.3 and 0.7, if you assume the 0.5 volt is the depletion, is the potential difference. So this is 5 into 10 to the power 6. So very high electric field, volt per meter, is produced in this depletion region. Very high electric field, right, is produced in depletion region, right? Okay, so this is the PN junction diode. This is the PN junction diode, you can say. Now this diode or the PN junction diode, right, can be used as a unidirectional current element, right? This is the P and this is N, right? So how to use this as a unidirectional current diode, current element, right? And it comes under the biasing of the diode. Biasing of diode. Biasing mean this is the unbiased PN junction. This is what? Unbiased PN junction. Unbiased PN junction mean no potential difference is applied. Are you getting or not? So biasing of the diode mean you have two, we have the two types of the biasing. First is forward biasing. Forward biasing. Forward biasing characteristics. In the forward biasing characteristics, suppose this is the P type semiconductor and this is the N type, right? And you add the positive terminal of the battery to the P type semiconductor, or you can think it is a diode. The same thing is there. This is the block diagram, this is the symbol of the diode, and here you will apply the battery. This is called the forward biasing, right? What happened by the forward biasing? First copy this, I will explain. So forward biasing characteristics mean positive terminal of battery is connected to positive terminal battery is connected to P side, and the negative terminal of battery is connected to N side. Do you understand or not? So it is the positive charge, the positive terminal supply the positive charge, and the negative terminal supply the negative charge. Do you understand or not? So when, listen one thing, when you connected the positive terminal, so it connect the positive, it supply the positive charge. So this positive charge is, this is the uncovered ion, the positive charge in terms of hole, they are stick with this, and from this the electrons, the negative charge, stick with this. Do you understand or not? So therefore this ion are neutralized. Do you understand? Right, very good. Initially when nothing is applied, right, the depletion width is like this. Understood? When you connect the positive charge, it will supply the positive charge or not, util, and it will supply the negative charge to this side. Are you getting? So positive charge is supplied in terms of holes, so it supply the holes and it supply the electrons. Are you getting or not? So when it supply the holes, these holes, the number of holes are going this side, and in this side the electrons are going. So these holes combine with this uncovered ions. Are you getting or not? In the same way, these electrons are combined with uncovered positive ions. Are you getting? Sanjay? Not getting? Repeat. Yes. So when, okay, so when this electron, this uncovered ion is combined with holes, so this is neutralized or not? So this is also neutralized, this is neutralized. So neutralized. So therefore the depletion region, initially when this is n side, p side, this is the depletion width. When the positive charge, the holes are supplied, and this is the electrons are supplied, so the width of the depletion region is reduced. Are you getting or not? So when the depletion width or depletion region width is reduced. Do you understand or not? This is p side, this is n side. So here negative ions, here positive ions. So initially it was the negative depletion region, it is the positive depletion region. Are you getting or not? So it is more, it is less. So if the depletion width is reduced, the potential difference is also reduced. The depletion width is reduced, right? Therefore barrier potential is also reduced. Do you understand or not? The barrier potential is also reduced. Understood or not? Barrier potential is also reduced by battery potential, right? By delta, right? So if the barrier potential is reduced, so these are the holes. Getting or not? And these are the electrons. So if depletion width is reduced, what will happen? The hole can jump to this side. The hole can jump to this side. Do you understand or not? And the electron can jump to this side, and the electron can jump to this side. Barrier potential, therefore the barrier potential is reduced, and holes can diffused to n side, and electrons can diffused to p side. Are you getting or not? Right? And what are the types of the n? what are the types of the carrier? These are the majority charge carrier, these are the majority charge carrier. These are, and therefore when holes are moving this side, electrons are moving this side. So in this circuit, if you measure the current start flowing in it. Are you getting? Holes are moving this side, electrons are moving this side. Are you getting? So these are the majority charge carrier, right? So therefore this current, so therefore diffusion of majority charge carrier of majority charge carrier takes place and current start flowing. This current is called majority charge carrier current. Do you understand this thing or not? You tell. Why the diffusion takes place? Because by applying the forward biasing. Okay, so I'm explaining this once again, right? Listen one thing. When nothing is applied, there is a depletion region. In this case, the uncovered ion, negative ion, and covered positive ions are present. When you apply the battery, the positive charge are supplied to this side, and these holes combined with ions like this, they combine with ions and these ions are neutralized. Are you getting or not? So but these ions are not neutralized. In the same way, the electrons are supplied. If the electrons are supplied, these ions, positive ions, combine with this electron and these ions are neutralized. So depletion width, initially depletion width is more. When you apply the battery, the depletion width is reduced. Are you getting or not? Right? So depletion width is reduced. So therefore, if the width is reduced, the potential barrier to cross the majority charge carrier is also reduced. Therefore, the holes start flowing, or the diffusion of the holes start from p type to n side, and the diffusion of electron takes place from n side to p side. Therefore, a current start flowing in this circuit. This current is called the majority charge carrier current. Do you understand or not? Holes are diffused, electrons are diffused. What is the diffusion? Due to the concentration difference. Here the holes are in majority and here holes are in minority. So the high concentration charge carrier move to the lower concentration charge carrier. Do you understand this thing or not? You tell. Right. Any doubt you want to ask? Okay. So now I will discuss the reverse bias characteristics. Right. Now I will discuss the reverse bias. Wait for 1 minute. If I draw the current in this forward biasing, the current, right, versus potential difference. This is the potential difference. This is the barrier potential for the silicon. What is the barrier potential for the silicon? Say 0.7 volt, and for germanium it is 0.3 volt. Right. This is the current versus the diode current versus potential drop. For the germanium, the cutoff potential is 0.3 volt and this is 0.7 volt. Are you getting? This is the barrier potential 0.7 volt for silicon. If you apply this barrier, if this battery less than the 0.7 volt, the current does not flow. Do you understand this thing or not? And after that, the current start flowing in this case, and this is called the majority charge carrier current, majority current. Right? Please copy this. This is the majority charge carrier plus diffusion current. Diffusion takes place. Right? This is the diffusion. Now I will discuss the reverse biasing. In the reverse biasing, what will you have to do? Suppose this is the diode or the PN junction, this is the P type, N type, right? This is the unbiased, right? Unbiased diode. Here, this is the negative ions, this is the positive ions. Are you getting or not? In the reverse biasing, we connect this PN junction diode such that, right, the positive terminal of the battery is connected to the N type and the negative terminal battery is connected to the P type. So it supply the holes, it supply the electrons. Do you understand this thing or not? When the electrons are supplied, so the number of electrons are increased. When it supplies the positive charge, the holes, so the holes are again increase in this side. Sanjay, is it clear or not? You tell. Right, if you connect in this way, right, the holes are supplied, so this is the positive and negative ion, these are the uncovered ion, these are the covered ion, like this, right. In this side, when the holes are supplied, they combine with this and again the uncovered ions are produced. In the same way, when the electrons are supplied, so there are the uncovered ions, like this, right, like this. So in this case, the depletion width is increased. Do you understand or not? You tell. Depletion width is increased. So if the depletion width is increased, you tell, the diffusion is possible or not? You tell. Diffusion. What is the diffusion? You tell. Is not possible. Because what is the diffusion? The movement of the charge carrier from high concentration to low concentration. The potential barrier is increased. Depletion width is increased. Potential barrier is increased. Do you understand or not? And diffusion is not possible. If diffusion is not possible, well, then what happened? You tell. No, yes, there will be no current definitely, but listen, one important thing. Diffusion is not possible, rather drift starts. What is drift? Listen one thing, make the figure little big. The depletion region is increased. Are you getting or not? And the symbol you can make for the diode, this is the symbol of the reverse biasing. Are you getting? Listen one thing, at every temperature, here it is the negative ion, right, and this is the positive ion, right, this is the positive ion, right, and the electric field is in this direction. Do you understand this thing or not? Here holes are in majority, the electrons are in majority. Is it clear or not, Sanjay? But the holes are also present, the electrons are also present. Do you understand? At every temperature, the covalent bond is breaking, right, and combining. Do you understand or not? The electron hole pairs are generated and they are recombination and recombining. Do you understand or not? At every temperature, covalent bond is breaking and recombining. Electron hole pairs produce and they recombining. Do you understand or not? But as soon as the electron and hole pair is produced in this region, utal. The electron and hole pair is produced in this region. Suppose this is the hole, this is the electron, this is the hole, this is the electron. Getting or not? So this electron and hole, when it is produced in this region, they are in the very high electric field. Are you getting or not? They are in very high electric field. Listen, if an electron and hole pair are produced in this region, so at the same time the another electron and hole pair are produced and they are recombined. Getting or not? So here the no electron or hole pair is in excess, because they are the rate of production of electron hole pair is equal to the rate of recombination. But in this case, as soon as when a covalent bond is broken, the electron and holes is produced. Do you understand? And they are in very high electric field. So because of this electric field, electron start moving in this direction and the hole start moving in this direction. There is no time to recombination process. Do you understand or not? As soon as the hole is produced, they move to this side and the electron is moved to this side. Do you understand or not? This hole combined with this electron. Are you getting? And this hole combined with the hole. What is the hole? The minority charge carrier. What is the electron? Say minority. So there is a electron deficiency. So this electron is supplied by this side. If this hole is combined with this electron, one hole is supplied with this side. Are you getting or not? So the majority charge carrier does not move. Rather, what start moving? The minority charge carrier. At every temperature, covalent bond is breaking and recombining. But when a covalent bond is broken in depletion region, they are right. Electrons and holes are produced, and they are in the effect of very high electric field, and due to this electric field, they are drifted from depletion region. Are you getting or not? And yes, copy this first. So when the reverse biasing, we apply the reverse biasing, so the minority charge carrier start moving, right? Due to they are drifted from depletion region, right? And the very small current start flowing in it due to minority carrier. This is called drift current, right? This is called drift current. Do you understand or not? Right. So if we make the graph for the current and the voltage, if the voltage is negative side, very small current start flowing in it. Very small. Are you getting? How much it is small? This is the very small. Although this is the forward characteristics, and this is the reversed bias characteristics, right? And this current is in nanometer. For the germanium, this current is in nanometer. For the silicon, right, this current is in microampere, my nanoampere, and this is microampere. Are you getting? So this is what? Say drift current plus due to minority charge carrier, and this is called the reverse bias characteristics. So when the reverse bias when the battery is applied such that it is N and P side, so this is called the reverse drift current. This current is called the reverse saturation current also. This is called drift current or reverse saturation current. Reverse saturation current. Are you getting or not? Listen, one more thing. In the forward wise, when you increasing the potential, the current is also increasing. But in the reverse bias, when you increase this potential difference, right, you cannot increase the value of the reverse saturation current. Why? Because the minority charge carrier are present in limited number. Are you getting or not?